study of the gas laws, we're going to look at Charles' law. We're going to include some applications as well as look at a couple of experimental ways of proving Charles' law to help you understand it very much better. And so in the gas laws, we're actually looking at pressure, volume, temperature relationships, and we're just going to start by studying two of those three and keep the third one constant, as well as the amount of gas, the number of moles. So what is constant in Charles's law? If we look at this table, we discover that for all the gas laws that are here, Boyle, Charles, and the pressure law, the moles are constant, but in Charles's law, the pressure is going to remain constant. And the first thing I want you to think about and maybe write down the response, you've got a setup with water at cold tap temperature, and then that's being heated. What will the balloon look like after it's been heated? And explain why you think any change has occurred. So for Charles' law, we're going to investigate the relationship between volume and temperature, V and T, and we're going to keep pressure, P, constant, and N, the number of moles, constant. Something else for you to consider here. Got a regular party balloon filled with helium. Describe what's happening to the particles inside the air, inside the balloon, as it floats in air. And another item to consider, here are two balloons. The first one is in an environment at 65 degrees Celsius, and that's really quite hot. It would be water too hot to touch with your fingers. And it's being cooled down to 1 degree Celsius. And no gas is being removed, the pressure will be kept constant. Explain why there is a difference with reference to the particles inside the balloon. And in the Charles Law Lab, it's going to be a data collection activity. If you were doing the lab, you'd have to wear goggles, lab coat or apron, and be very careful with the hot objects as we're heating materials. We're going to start off with the apparatus that's on the right. You've got a balloon that's anchored at the bottom of a beaker of water with a weight, and a thermometer to take the temperature of the liquid. And what you're going to do throughout the examples that are here, you're going to note the diameter of the balloon for 5 different trials at different temperatures. First one here, it's nearly immersed in a ice salt bath. You can see the diameter there, and you can read the thermometer, and you are going to collect the data, so you will need a data table. So you can pause to be able to start your data table with this is trial 1, and read your temperature carefully. So again, pause this if you haven't got a results data table, because you've got more data and numbers than you're going to remember in your head. So for trial 2 and then trial 3, we're going above room temperature now, equipment sitting on a hot plate. Again, care with the top of the hot plate. And at the end of the lab, make sure it cools down after you turn it off before you put it away. And again, keep noting the diameter and the temperature in each. So we've got 2 more of these. You can pause them to get the information and to write it down. And once you've got your data table, and if you were doing this in the lab, you would collect qualitative data, you would describe what you would see, as well as the numerical quantitative data. Now, just look at the table that you've written. Are any trends apparent? So a simple overall conclusion without going into a deeper analysis at the moment. And you can pause while you do that. We can analyze it further by drawing a graph, but we're going to do it in a slightly interesting way. Your graph paper, you're going to turn through 90 degrees, and in the top right-hand corner, that's where you're going to draw the graph, and hopefully you'll see exactly why we're using just a portion and that portion in a bit. Now, you're going to plot the volume of the balloon in centimetre cubed versus the temperature, and we measured it in degrees Celsius. And so we've got the formula for the volume here, but remember, you've got an R in there for a radius, and you noted the diameter. So why do you think you're measuring the diameter, not the radius, in the lab, if it's really the radius that we want? And so here we are with the axes labelled, the zeros for the volume, the zeros for the temperature, and you're going to plot it. And so what does the shape of the graph show? So lines can have different formulas. If it's a straight line, you've got the equation for a straight line, the relationship between x and y values. If it goes through the origin, then x is directly proportional to y, which is what we can write. Now, your graph, guessing here, is not going through the origin, and what we're going to do is rework the origin. You're going to extrapolate, extend the line of the graph backwards to the left with a ruler, so it's going to go through the x-axis. And the point at which your line of the graph goes through the x-axis is your experimental value of absolute zero, the temperature where the gas has no volume. Talk a bit more about that later too. So this is in essence what you've got, what you're looking at, and you will put the scale on going into negative degrees Celsius values in order to get the point at which your line goes across the x-axis, which is 0 Kelvin, the Kelvin temperature scale. So for the Kelvin origin, where your extended line goes through the x-axis, you now have a direct proportionality between volume and temperature, provided the pressure and amount of gas, number of moles, are kept constant. So the extended temperature scale 0, you have proportionality, and at the bottom here it says gas volume is not proportional to Celsius temperature. So we're looking at a hot air balloon. So as it starts, haven't fully inflated the balloon maybe, going to use a heater, usually propane heater, to warm the air, and the gas particles are going to move faster, and the canopy will stretch and become full. Larger balloon is formed, full-size balloon, displacing more air. The hot air is less dense indeed, and the balloon will rise. So there's another way to get to Charles' law, and here we're going to use some air trapped in a tube and look at how essentially this big bubble of trapped gas changes when it's heated. And here's the apparatus. So immersed in water again, because that water bath is going to provide the temperature for your measurement to take place. And you've got a melting point tube which has a liquid which traps the air in the tube. And your teacher would have prepared those for you. If you're doing the lab, that would be concentrated sulfuric acid. And behind the tube, a little bit dark here, you've got a ruler, and so you can actually measure the height of that air bubble, the trapped air beneath what here is that black liquid, the sulfuric acid. And you're going to heat the water, and you're going to take the temperature about every 10 or so degrees Celsius rise up to 75 degrees Celsius, but note the exact temperature for when you measure the height of the column. So here, some safety if you were doing the lab: goggles, gloves, lab coat, apron, and again, care with the corrosive liquid, the acid in the tube, and the hot apparatus. So you can here you can see an expanded version, and the height, what is actually measured to get your data. And you're going to change the temperature 5 or 6 times. And here is a set of data, and you can again plot that data in the same way as you did with the balloon experiment for Charles Law. Have your graph paper with the top right-hand quarter, when it's landscaped, paper's turned essentially on its side, and here we're going to plot before volume and temperature, but here we're actually plotting the height. So we can use the height because height times surface area in the tube equals volume, but the tube has a uniform internal surface area, so the volume of the tube itself is proportional to the height. So you can plot the height measurements against temperature in Celsius, and again extend the graph. You might need to add graph paper to the left and a bit of sticky tape to extend the graph, extrapolate it back to the left until it crosses the x-axis. And here one has just been dotted in, only 4 points here, getting the straight line, and then using the scale into the negative values to determine absolute zero. So if you've done both of these exercises, you've got 2 different values. But again, the slope of the graph, the line of the graph, doesn't go through the origin in the blue portion. So the height is not proportional to the Celsius temperature again, but going back to the Kelvin scale, yes it is. And a little aside here about the Kelvin temperature scale. So each degree change is equal to a temperature change in degrees Celsius, but the actual value of the readings, they're not the same. 1 degree Celsius, which is just above the freezing point of water, is not the same as 1 Kelvin, the freezing point of helium, negative 272 degrees Celsius. So when you want to convert Celsius to Kelvin, add 273 to the Celsius value. So boiling point of water in Celsius is 100 degrees Celsius. In Kelvin, add your 273 to get 373. Now you're going to look at those 2 methods. What do you think the advantages of using method 1 compared to method 2? So the balloon diameter change versus that height of the air column change. And you now know what the conversion number is. You may look at which gave the better one, and what are the disadvantages? So there's going to be more than one. So which method are you going to choose as the one that you would prefer to use, and why? So if we look at Charles' law in words, the volume of a fixed mass of gas is directly proportional to the Kelvin temperature, provided the pressure remains the same. And we said it's a fixed mass of gas, so N in moles is the same as well. So that's in words. If we look at it in letters, mathematically, you've got a straight line that goes through the Kelvin temperature scale origin. So volume is directly proportional, squiggle, T, or V equals KT, where K is a constant and is the slope of a graph, a straight line, going to be the same all the way along. So if I pick a point 1, so volume 1 and temperature 1, could be the first trial that we did. The other one should say the second trial or the fourth trial, doesn't matter. As you process it, V1 over T1 equals the slope, and V2 over T2 equals the slope. So V1 over T1 equals V2 over T2. Now, comes with some other statements. T, temperature, has to be in Kelvin, and the pressure has to be constant, and the amount of gas, the number of moles, has to be constant. So we've got an example here. You can calculate how a volume will change at a different temperature. So a party balloon got a volume of about 33 litres at sea level and 22 degrees C. What will its volume be at an altitude of 5,000 meters, where the temperature is negative 16.7 degrees C? We assume the pressure doesn't change. So in reality, it would have to be taken up in a pressurized container. Also assume the same number of moles. None escapes, none is added. So define the variables every time, and you'll never get a calc wrong. Well, you might do some incorrect copying and other things, but list the variables. V1 equals, keep the unit with it as well. V2 is my unknown, my question mark liters. T1, my temperature, but it's in Celsius, so I have to add the 273 to get 295 Kelvin. I do the same with my negative 16.7, add that to 273 to get the Kelvin value, and now solve, put those numbers into the Charles law equation and solve for V. Oh, now it's less than it was at sea level. Is that what you would expect? And finally, we'll just look a bit about Jacques Charles. Born in 1746, he developed and designed balloons before anyone had flown in balloons. He first flew on the 1st of December 1783, and it was about, just under 2 weeks after the first manned balloon flight, also in France. Now, the first manned Montgolfier balloon used hot air, heating the air with hot coals with an enormous paper balloon canopy. Charles' balloon was a closed, sealed hydrogen balloon, and actually made the hydrogen 1/2 ton of scrap iron, 1/4 ton of sulfuric acid, and you've got the equation there because we're chemists. It started in Paris. So Charles and Nicolas Robert flew just over 22 miles at an altitude of over 500 meters and came down fairly gently. And aside from ballooning and doing gas law calcs, he invented a hydrometer measuring relative density, specific gravity of liquids, like alcohol, a ballooning valve to vent gas for safe descent, which he obviously was using, and he collaborated with Benjamin Franklin, an American scientist, who, along with 400,000 others, observed his first flight. So that's a summary of Charles's law.